Thank you. Great to see everyone.
It's great to see so many happy faces.
Tonight is a first. It's the first time that the London Institute has hosted an event in this historic lecture theatre. For those of you who don't know who we are, the London Institute for Mathematical Sciences is Britain's only independent research centre for physics and mathematics. Scientists have been crying out for a place where they can dedicate themselves full-time to what they do best, making fundamental discoveries. They don't get to do that at universities. At the London Institute, we speed up discovery by letting scientists do science full-time. Think of us as a place for full-time Penroses working at top speed.
So in February this year, we're so honored to be invited here to move into the Royal Institution. And in fact, the London Institute occupies the very set of rooms that Michael Faraday used to live in. It's right there upstairs. Okay, so we're not the Royal Institution, but we're at the Royal Institution.
The second way this is a first is the first time that Roger Penrose has sat down in casual conversation with mathematicians to talk about his science, himself, and the way his mind works.
Right. So for those of you who don't know who Sir Roger Penrose is, you're clearly at the wrong event. Martin has kindly pointed out where the exits are, so just please leave quietly. I'm very privileged to have known Roger for a number of years as a colleague. And in 2019, I was so delighted and honored that Sir Roger wrote a chapter as a contribution to my latest book, Topology and Physics. And when Roger turned in his exquisite chapter on singularity theorems, which we're going to talk about shortly, it confirmed a suspicion I had a very long time. Surely this man is going to get the Nobel Prize.
Sir Roger is a mathematical physicist with the eye of an artist and the soul of a philosopher. He's also a master wordsmith capable of turning very complex ideas and making them look simple. He's also been an inspiration for a generation of physicists and mathematicians alike.
Right. So nobody's left, so I guess everybody knows that Roger Penrose did indeed receive the Nobel Prize in 2020 for physics. But you may not know that he also is the holder of OM, which stands for Order of Merit. So I'm going to do a little bit of calculation for here on the board. Chalk on blackboard. This is what we do at the London Institute. It's like kids in a candy store. This is what this is all about. So here's a calculation for you, okay? So the Nobel Prize was founded by Alfred Nobel in 1901. The OM, Order of Merit, was founded by King Edward VII around about the same time. To date, there has been 962 recipients of the Nobel Prize, of which there's approximately 120 alive right now. The OM has gotten 196 in its history, and by definition, can never exceed 24 living members. Therefore, by both measures, you can clearly see that the OM is about 5 times harder to get than the Nobel Prize.
On that
and
note,
Sir Roger has both.
On that note, can you join me in putting your hands together to welcome Nobel Laureate Sir Roger Penrose, OM. Thanks for joining us. Really great to see you. Today's the first time we met, so it's very exciting for me.
Thank you.
Welcome to LIMS and the Royal Institution.
It's nice to be back.
Yes, indeed.
Yes.
So maybe, if you don't mind, we can just kick right into the topic about the topic of black holes, for which you won the Nobel Prize. So could you possibly give, for a lay audience, some of the background? Let's go start at the very beginning of our journey. some of the background, what were the thoughts about black holes and general relativity when you got interested in the subject?
Ooh. Well, there was a paper published in 1939 by Oppenheimer, the same one of atomic bomb fame, Oppenheimer and a student of Snyder. And they wrote this paper, which was about a dust cloud, so there was a spherical ball of dust, which had reached a level where it could collapse inwards through its own gravitational field, and it would go inwards and inwards and inwards, and the picture was what we now think of as a black hole. This was in 1939, just before the war, and since the body was, well, first of all, what's dust? Dust meant a material which has no pressure. So there's nothing to stop it from having pressure. Secondly, it falls radially inwards. It was exactly spherically symmetrical. So the fact that it meets in the middle, and when it gets into the middle, the density becomes infinite. And so when the density is infinite, you get to what's called a singularity, where according to Einstein's theory of general relativity, the space-time curvature becomes infinite, and so you have nonsense at the middle. And so this picture was around at that time. I don't know that people took it very seriously. It was an idealization. You had to get this big cloud of dust, it had to fall pretty far in towards itself, and it had to be no pressure. It had to be exactly spherically symmetrical, aimed towards the central point. So the fact you got this infinite density and therefore infinite curvature in the middle was not a surprise. This paper was lying around for quite a while. I did know about it. I was in Princeton I went to Princeton in 1959-60, and 1959-60. And John Wheeler, I went to work with him, and he was one of the people who was really interested in this issue of what's called gravitational collapse. But it was taken as a very theoretical thing. But the excitement really came, I think it was in the early 1960s, or perhaps slightly earlier than that, when these objects called quasars were discovered. Well, I don't know whether you could say the objects were discovered. The signals from them were discovered. These were radio signals, and they were of such an intensity, and also they were redshifted. That meant that they either came from something very, very dense, or more likely were taking part in the expansion of the universe and were extremely distant. So these objects seemed to be extremely distant and extremely energetic. They were emitting more energy at that sort of distance than from, 1,000 galaxies or something like that. A large amount, enormous amount of energy. But also they couldn't be extraordinarily large either, nothing like the size of a galaxy, because the radiation was varying to a degree which indicated that it couldn't be larger than the solar system, at least, probably a lot smaller than that, in order that if it could change in intensity sort of in a coherent way, one part couldn't communicate with another if it took so long for a light signal to get from one side to the other. So it had to be relatively small, considerably smaller than the galaxy. And so people began to wonder whether these weren't objects of this sort of size and concentration that you have in this Oppenheimer-Snyder picture. The trouble is that picture, just everything falls into the middle, nothing comes out, you wouldn't get any signals coming from it. So it couldn't be just that. Might be something more complicated, swishing around in some way. And that was a question that was raised. I know Fred Hoyle and various colleagues of his were toying with the idea that there wasn't perhaps there was some body of the kind of scale that we would think of as a black hole. The terminology hadn't arisen, and they couldn't be spherically symmetrical, otherwise you wouldn't get these signals coming out of it. At least it couldn't be a black hole in that sense. What's more, at that time, when I say at that time, I mean, I just think when it was, 1964, I guess, there was a paper written by two Russians, Lifshitz and Kalatnikov, and they had an argument to show that in the general case, according to Einstein's general theory of relativity, in the general case, you would not get singularities. So if the density or curvature started to get too big, it would sort of swirl out again. And you wouldn't get singularities. And that was a paper they'd written. And John Wheeler was very interested in this question of gravitational collapse. And I wasn't actually working with him at the time, as far as I remember, but he certainly, earlier when I was working with him, he was interested in this question of collapse. And I began wondering, well, if it is complicated and irregular, do we believe what the Russians say, that it's not going to go singular? I had a look at the paper. I was not completely convinced by the methods they were using. It didn't seem to me they were pretty watertight. Right. There was actually a serious mistake in the paper. I didn't know. I didn't see the mistake, which they later corrected. But at the time, it seemed to be the case that you would not get these singularities. But as I say, I was not totally convinced by the argument. So I began to think about this. I began to imagine what it would be like inside one of this swirling and collapsing stuff. Right. And I tried to think of some way of characterizing it having reached a point of no return. Right. I didn't have a good characterization at the time, but I had written a paper. This was a paper on something different, which I'd sent to the Royal Society. It was about gravitational fields and electromagnetic fields and what they behaved like when you went very far away. And as part of the argument, I needed to have a result. I won't go into it, but I thought you might as well just assume this result. It's pretty obvious to assume it. But nevertheless, I thought perhaps you could prove it. And in an appendix, I put an argument in which used the type of argument which turned out to be useful for this black hole problem. I wasn't thinking about that problem at all. I was just thinking, like, if you have some region in space-time and you look at the future of that region. So when I say by the future of that region, I mean if you have all particles starting at that region and they're going, if you like, as fast as they can away from it, what kind of a region do they trace out, and what's the boundary of that region look like? So that's the sort of thing I had to think about. But I had no way of seeing how to apply this to the black hole problem. Now, I happened to be, at the time, this was in 1964, and I happened to be working. I lived in Stanmore, so I came in on the tube, and I think I walked through the woods to get to the tube station. I came on the tube, and I was walking towards where I worked, which was at Birkbeck College. And I was accompanied by Ivor Robinson, who was a good friend of mine. He was an Englishman who happened to be working in Dallas, Texas. He had this wonderful way with words. I didn't know anybody who played with words in the way he did. It was just fantastic. And the Americans all loved him. It was just so different from their way of speaking. He's a very clever chap, and he had worked on solutions of the Einstein equations using very ingenious methods and things like this. So he was talking to me and waving his hands around in his normal way about something which I've completely forgotten, I'm afraid. Probably something about his solutions in general relativity or something. Anyway, it was very interesting. And we came to this side road. I think it was Mallet Street. I can't remember exactly. It was somewhere near Birkbeck College where I worked. And we came to the side road, and we had to check there was no traffic there. And so the conversation stopped. We got to the other side, and then it started again, talking about all this stuff. And then he went off. He had to go off somewhere. And I remember having this strange feeling of elation. So why am I feeling like this? I didn't know. So I went through all the things. What did I have for breakfast? Was it anything to do with that? Was it the walk through the woods? Don't think so. Catching the train? No, I don't think so. I just through all the things. And finally I got down to this place where the conversation stopped and I crossed the road. And I thought, gosh, I had an idea then. Almost lost it altogether. But I had this idea, which was what I called a trapped surface. And this was basically a surface. You see, you had to have a criterion which didn't depend on the symmetry. Because, sure, if it's just symmetrical, then everything goes into the middle like this. And what does that mean? Because in a real situation, it would swirl around and probably not do that. That would be the normal view. But the thought I had was this thing I called a trapped surface. And it's this kind of surface, it's a spherical surface. That means it has the topology of a sphere. It can be wiggly. It doesn't have to be exactly a sphere.
In fact, I think I have this. This is
Well,
your
that's
paper.
Yes, that's the picture from, I think I can see it.
You can see it from there.
Yes. Well, actually, I can't see that. My eyes are not good enough. But I can see this one.
So the audience can see.
Yes. No, I know what it is.
Right,
Yes.
right.
Yes, that little black ring in the middle. You have to imagine, of course, that you've got one more dimension. This is only a 2 plus 1. That is 2 space and 1 time dimension. The time is going up. Space is going round. But you've got to have one more dimension, and that thing that looks like a ring in the middle is really a sphere. When I say it's a sphere, well, it is a sphere. Right. But you imagine a flash of light coming instantaneously over that sphere. And because it's, well, what's called inside the horizon, there's that cylinder that you can see going up. That's where I could talk more about this details of this picture, but let me not, because it'll take too long. But a flash of light on that thing that looks like a ring would be focused inwards. So the flash would, not just the inward, you see the flash would, there'd be an inward flash going inwards, and there'd be an outward flash, but the outward flash is going in too. That is to say, it's focusing inwards. So the light rays are converging, they're coming towards, they're going inwards. And I knew once you had that situation that the future of that, what I call the trapped surface, and the boundary of that future would have certain properties that even if it was wiggly, it's not the exact picture. You imagine it wiggly, but don't wiggle it so much that the convergence becomes a divergence. That's all. You just keep the convergence, what you see. And then the boundary of that future has to have certain properties that it would have to be what's called compact. It would have to close in on itself. The light rays would have to start crossing themselves in complicated ways. And because of the work I'd done on this other paper in the appendix that I thought was a complete waste of time, I don't know why I've even bothered to do it, it's just sort of a, you know, get that feeling sometimes, you know, maybe I can do it, and so maybe I should. I don't know if anybody ever read that. I think somebody did read it and told me it was wrong. It might have been wrong for all I know.
But I just want to emphasize to the audience, this is it. 3 pages, you get the Nobel Prize. This is probably one of the shortest articles ever to get the Nobel Prize. This is the entirety of the paper.
It should have been slightly shorter, too. Because I used an argument which was... Charlie Misner was a mathematical physicist I worked with at Princeton, a very clever fellow. And he certainly picked up on this thing very quickly. And he pointed out a simplification to the argument.
Oh, gosh, right.
He was quite right. I should have done it his way. I just didn't think of it at the time. It wouldn't have made it much shorter in the paper, but conceptually much shorter, yes.
So you have this idea that these singularities must exist.
Yes.
Could this have been taken not as support of Einstein's general relativity, but the opposite, as evidence that it's too absurd to be true?
Well, it's very curious, and I often wonder what Einstein would have thought of it. You see, unfortunately, he died before this came up. But I do remember I was visiting Princeton not that much later, and this result, I guess, was beginning to be accepted by people. And Bob Dickey, who was a very distinguished theoretician and experimental physicist that worked at Princeton, and he had his own ideas, which were slightly different from Einstein. He wanted something to be wrong with general relativity. He came and he slapped me on the back and said, "You've done it. You've shown general relativity is wrong." So that wasn't quite what I thought I'd done, but still. What he didn't realize is that the same argument would apply to his theory. But maybe I told him later. I didn't know enough about his theory to know that the same argument would show. So you definitely get the singularities. It doesn't tell you what they look like, the singularities, or whether the curvature goes to infinite or something else funny happens. It just shows that something goes wrong. And what it is that goes wrong, one could argue about. It does not quite say that you get black holes in general situations. It tells you get singularities, and there is something more horrible that could happen, which are what I call naked singularities. Those are singularities that you could actually see, and the information could come out from them. As far as I'm aware, there is as yet no proof that in general case you don't get naked singularities. I put this as a conjecture, which I call cosmic censorship. that somehow they, the good Lord or somebody or other, or what it would be, didn't like these ideas, and they were sort of clothed in these singularities, in these event horizons, so you couldn't see them. But that's what gave you a black hole.
Right.
It took a while, I think. Various people, not just Bob Dicke, but I remember Phil Morrison, who was a very distinguished physicist. And I remember talking to him, and he said he didn't believe in black holes. And I thought, why? And he said, well, he didn't believe in general relativity. It was not that well confirmed. The evidence in favor of it's now extremely good. There's a lot of extremely good evidence in favor of it. But at the time, there was, plausible reason to doubt it. And my guess is that that's what Einstein's reaction would have been. In fact, he did consider situations with stars going around in some complicated way, and they ought really to collapse inwards, but he had them orbiting around in a way that he thought would stop them collapsing. Right. So that he was trying to prevent this kind of situation. But he was also working on these unified field theories, which were trying to go more than encompassing gravity, encompassing electromagnetism and other fields too. Right. And he thought that general relativity was just a step in the route to these other theories. And if it went wrong because of singularities, then so much for the theory.
Right.
I'm just guessing what he would have thought.
When this came out in '65,
yes.
To what extent did you think there would be experimental or observational confirmation? I mean, perhaps in your lifetime or soon.
There were some ideas about detecting gravitational waves, but detection was much too primitive. And Joe Weber had an idea, and he had a machine which he thought was detecting gravitational waves, but that was not true. He was over-optimistic. I thought he might have been right too, and I was wrong. I remember being corrected by the then Astronomer Royal, said you shouldn't believe Dicke. No, we shouldn't believe Joe Weber. No, that was an interesting time. But it took a long time for the black holes to be accepted. I seem to remember going to these conferences. They were called Texas conferences on relativistic astrophysics. And I went to the first one. I think that was before this theorem, was it? I can't remember. And then there were others. And I got invited to a lot of them to talk on these things. And it was quite curious because belief in black holes was very much a minority activity for quite a long time. And when you could see it creeping up and creeping up. And when it got to 50%, then it sort of shot up. And people took them seriously.
Right, indeed. And I mean, especially right now, I mean, with LIGO and detection of gravitational waves, it's very much topical, like right now.
Yes, well, the evidence. Well, of course, there's people who I shared the Nobel Prize with, who is wonderful. I used to use as examples. You can see, not quite in real time, but you can speed it up. And you can see the stars going around near the center of our galaxy, right in the center, and you can see they're going around and they're following these elliptical orbits. When I see this, I think, oh gosh, Kepler was right. So you can see these ellipses, and they speed up just at the right time, and there's got to be a mass right at that focus. You can't see the point, but all these other stars are going around the same way. Oh, I think it's a stunning observation to see these things going around. You see, there's got to be something really massive in the middle there. So of course, that evidence wasn't there at the time.
It took a while for the Nobel Prize Committee to catch on the evidence.
It took a while, I suppose you could say that, yes.
So how did you find out that you got the Nobel Prize?
But it happened.
Well, that was an interesting occasion, yes. I think I was having a shower, I just can't remember. And the phone rang, and this was my PA, PA, this Petrona Winton, and she was phoning me up, and she said she'd got this inquiry from some Swedish people who wanted my phone number. And she said, I don't give his phone number out like that to people.
Yeah, we've noticed.
So she told me, when I come out of the shower, and I spoke to her on the phone, and I said, no, she told me about this thing. I said, well, who are they, these phone jobs? She said, I don't know. It's the Swedish people. And I said, well, I suppose it can't be any harm giving the phone number. I suppose it's all right. So I waited. It was quite a long time. And then the phone did ring. And this chap, so he was the president of the Swedish Academy of Sciences. And he started to talk to me. And he said, oh, wait a minute. I'm called away on another phone. So I was sitting with my phone and waiting and waiting and waiting. It took ages and waiting. I have no idea. But I thought, well, look, if this is really important, he'll call me back. So I hung up. So he did call me back. I think he was trying to get hold with the people in America. Well, there was one in Germany and one in the US. And then one in the US, I guess it would have been very early in the morning. So people don't usually mind being woken up to get a Nobel Prize. But, no, I had sort of begun to guess it might be something like that, but I wasn't sure about it.
Now, if you don't mind, Sir Roger, I thought we might shift gears a bit.
Yes.
So I think I heard you're writing a book. I think you mentioned to me you're writing a book. Well, multiple books. There may be three, but I think I know of two or three. But one of them is called Astromatics, I think.
Yes.
MC Escher is a graphic designer, Dutch graphic designer, who would do things with impossible shapes and played around with some of the different ways there are to tile the plane and conformal maps on those things. And so I think he had an effect on your thinking, and then your thinking went on to have an effect on his thinking. So if we could go back to the beginning and hear how that started in the first place.
Yes, well, this was a little bit before the stuff on the Nobel Prize. I first came across Escher's work because I think I was in my second year as a graduate student in Cambridge in mathematics, and a particular colleague of mine said, let's go to the Amsterdam where there is the International Congress of Mathematicians was being held. So we both went, and I remember going to lectures which I didn't understand and lots of things like that. And I was getting on a tram or a bus, I think, and one of my lecturers had in his hand a catalogue of an exhibition he'd just been to. I said, what on earth is that? And this was this picture, Night and Day, of Escher's, where you see these birds across the sky, and they're black ones going one way into the day, and white ones going the other way into the night, and they interlock with each other. The gaps between them become the birds going the other way. And I looked at this thing, and where on earth did that come from? I said, there's this exhibition in the Van Gogh Museum by this Escher. Yes. And I went to, he said, you'd be very interested. So I went to the exhibition, and I saw all sorts of extraordinary things, including this one, which is called Gravity, I think. That's, is it called Gravity? That's
Relativity.
the one. Relativity, that's right. You've got the three different directions of gravity going in the picture. I remember that one in particular, which really, I think that one was the one that impressed me the most. But there are all sorts of amazing things. I'd never seen anything like it before. And I remember coming away from that and thinking I would try and draw something impossible myself. Not quite. Perhaps a little bit different from the thing I've seen. And I tried to draw a thing with with roads and bridges and rivers and things and going in ways which were inconsistent. And then I simplified it down to, it's not there.
Oh, no, we
don't have that one, I don't think.
You don't have that one.
The next one, the paper?
The thing which is called...
you mean this thing?
Oh, yeah. We
right.
actually have the entire paper.
We have the entire paper.
Oh, that's the paper, yes.
Yes,
That's right.
absolutely.
So I have a quick question for you, Sir Roger. Do you only publish 3-page papers? Because this one's also 3 pages.
But this is a
It's
special
true,
one you wrote
The
your
first
dad.
ones were pretty short, yes.
Right.
Yeah.
The first one I actually... the first thing I published was in Eureka. This was in the undergraduate journal, and that wasn't even a page. It was well, that was definitely less than a page, yes.
We need to go back to shorter papers.
Yeah, absolutely.
But I think the actual first paper published in a proper journal was about 3. It wasn't that much longer than that. That was a joint paper with a colleague. It was on algebra. But yes, so I simplified this thing with the bridges and the roads and came up with the thing left or right. That's on the, which way around are we? That way.
Well, you can see them there as well.
Oh.
Yeah, well, I'll point to this one.
Okay,
you can
yeah,
probably see that.
this one.
The triangle over there.
Yeah,
which
the tri-bar.
people call it a tri-bar now, yes. So I drew that picture. That was the sort of simplification of these roads and bridges and things. That was the kind of thing I came up with. And I showed my father. And he showed it to various colleagues, and they all kind of shielded their eyes. They couldn't take it. But Then my father started drawing buildings which were inconsistent and that sort of thing. And then he came up with a staircase. So I think that was a model he made, which was made out of wood. And I think the picture was... Anyway, so this was an article which we wrote. We didn't know what the subject was, but my father said that he knew the editor of the British Journal of Psychology, so we decided it was psychology. He thought that the editor would accept it because he was a good friend of him. So, and we gave credit to Escher. I think we're in the catalogue of his museum, said various things of that nature. He had in the meantime done something very like this. It was a thing called Belvedere, which was the same kind of feature. So he had independently come. And I should point out, as I'm sometimes reminded, that there was a Swedish artist called Oscar Reuterswärd, who did a thing with cubes stacked up, which was essentially the tribar. And he did staircases and things like that. I'm not quite sure when many of these things were done, but he was certainly doing it earlier than we were. But you can find things. There's a picture called the Jackdaw on the Gallows it's a Bruegel picture, which is a gallows, and you can see it's joined up the wrong way at the top. And people say, oh, he made a mistake. I'm sure he didn't make a mistake. Completely clearly, he was doing it deliberately. So other people did things like this. You have to find them in the right places.
I've noticed a very interesting coincidence that both Escher and your father Lionel have the dates 1898 to 1972. It's as if they had complete parallel lives.
They were parallel, yes.
And another coincidence is that Yang's first paper was written with his father, as it happens.
Yeah, it was in medicine, actually, so it's completely not in mathematics.
Yeah. I see. Yes, no, it was a great shame they didn't leave a couple of years later for a reason, yes. Or I should have done something a couple of years earlier. No,
So this got used. I mean, this got taken on by Escher himself.
Yes, well, Escher then drew, I think, ascending and descending with the staircase.
So we've got up above you that, and also the perpetual motion machine, the waterfall.
Yes, the ascending and descending was taken. That was the first one, and he sent a copy to my father.
Okay.
With a dedication on it. And then the waterfall, which he did later.
So it's an interesting case of art inspiring mathematics and mathematics inspiring art back again.
Yes. Yeah. Well, it was obviously Escher had a genuine feeling for mathematics, but it was particularly geometry. I mean, it's very interesting because, as you mentioned, there is this book which now with a colleague, I spend a lot of time not writing the book and occasionally giving lectures about what I would have been writing had I been writing the book. And finally, I think I was in giving a talk in Cyprus, one of these Zoom talks. And I got chatting to the people afterwards, and I mentioned the Astromatics book. And I said, it's got completely stuck and stymied. And they said, well, we know somebody who might be helpful to you. And they put me in touch with this young lady who is a graduate student in physics, and she lectures in physics. And she works in the United States. And I got in touch with her, and we are now collaborating on this book. So we have conversations pretty well every week.
Okay.
About Escher, and we find things which people have never... Yes, there's sometimes wrongly attributed in the sense that people don't quite know what they are. So I know we were talking about one of these Escher pictures, and we're trying to figure out what on earth it was. Finally realized, gosh, that's a great icosahedron.
Right.
And you see the description, and people hadn't noticed that's what it was.
So we've got a picture of the wallpaper groups, and a question for you, Sir Roger, is, was Escher aware of all the tilings of the plane?
He was. In fact, that's what started it. No, he did all sorts of pretty wild pictures, but they were mainly landscapes and quite wild, but not kind of impossible in this. Not periodic. He visited the Alhambra in Spain, and he was very taken by these different patterns.
Just for the audience, these are the only 17 crystals you can have in 2 dimensions. There are, 200 or 300 in 3 dimensions.
Yes.
But in 2 dimensions, you can prove this is all you can do in terms
That's
of
right.
tiles that fit together with no gaps.
And they're all in the Alhambra. People used to think there were only 16 of them, and then somebody found, nope, the 17th one is there too. So they're all there. And Escher became acquainted of these 17 different groups. And he illustrates them all. They are all in Escher.
Okay.
Right.
Yep.
Sometimes he illustrates more than one at the same time. It's clever. You see, you have it. If you take the colors as being irrelevant, then you get one of these. And if you take the colors as meaning these are different, so the symmetry has to give the same color into the same color, then you illustrate a different one of these groups.
Okay.
So it's quite clever. And the way you see, then there's another group, which is the group of the symmetry of the different colors. So that's sort of some mathematical ideas which we realized Escher was illustrating without knowing it, in a sense. So in the book, all these things will be described. But it's quite a lot of work. And
Yeah, I can imagine.
And of course, this ties very much with your famous tilings, the Penrose tilings. So yeah, go ahead.
Well, we have a picture, which you can't see, of the logo of South Bank University. Very big version of the logo.
I think
of
that
South Bank
reminds you of the
University.
story, perhaps.
Now, rumor has it, although I don't think it's in print anywhere, that this logo was an inspiration for some of your doodlings on aperiodic tiling.
oh,
That's got the pentagons around pentagons.
yes, I can see
So
it now. Yes, is that the City University?
Well, it's
the South
well,
Bank.
it's now called South Bank, but
It's
they have
probably
the pentagons.
changed its name, I
It
think,
may
yes.
well have done. It has changed its
Oh,
name.
yes, that's one of my embarrassing stories, yes. No, one of my faults was that I'm very bad at writing letters. And I'm afraid that affected my Escher correspondence too. So, but no, I was really very bad at writing letters. I don't know why. It's just one of these. Emails I'm a bit better at, but but I remember I had this letter which I hadn't replied to yet, and I think it was an invitation to give a talk by what was called the City University. And I think that pattern you can see of the pentagon in the middle and 5 pentagons going around it. I'm not sure if it was quite the same logo, because I think you could see in the one I was looking at, the outside pentagon is drawn. And so you can see that pentagon, and there are 6 pentagons inside, 1 in the middle and 5 around it. And they just fit snugly with the little triangular gaps all the way around. And rather than writing this letter and deciding whether I was going to give this talk or not, I started playing with that pattern and wondering what happens when you put the same pattern inside one of the pentagons. And then you blow it up to the previous side, and then you do it again. Then you get little gaps. And then you have to think of what to put in the gaps. And you can put more pentagons in the gaps. And you can get a pattern which has a nice, regular look to it. I learnt later that a Japanese person had done the same thing, and he had put the pentagons in the wrong places. Yeah, I'm not sure, when I see the wrong places, you wouldn't know it was the wrong places. And you can't tell from this, you have to go to the next stage. When you have to find some places, oh, sorry, you have gone to the next
I have
stage.
gone to the...
I don't think I can point exactly to where we go, but you have to see where the next... Is the one over on that side just pentagons, is it?
This is very much like the logo.
That's it,
Yeah.
yes.
Pentagons, yeah.
That's
Yes,
with
well,
the
that is
Jester's
the
caps,
example.
isn't it?
So you see pentagons, and then there are little rhombuses as gaps, and then there are little stars as gaps, and then there's what I call Jester's caps, 3-pointed stars.
This one.
And those are the 3 different shaped gaps. I think the Japanese man, when you did it his way, you didn't have such a systematic pattern as you went on. So you could keep on doing it again, and you don't need any more shapes.
Can you explain the significance of this pattern? Because we saw all the possible wallpaper groups, and this is a sort of a new sort of.
Well, first of all, it was just a pattern. And the pattern has this almost periodic character to it. You see, there's a theorem that the only symmetries you can have, if you want a periodic pattern, are, well, no fold, if you like, or one fold. You just got bilateral, or that's 2-fold symmetry, bilateral symmetry. Or 3-fold, that's triangles, or or fourfold, that's squares, or sixfold, which is hexagons. And that's well known. Those are the crystallographic symmetries. What you can't have is fivefold. But if you have this pattern, like the one over there, I guess, I can't quite see what the other ones are, then it's almost periodic. That is to say, what can one say about it? You take any region in that thing, no matter how big, you can find it appears again and again, infinitely many times in that same pattern. There are all sorts of ways of saying it. Or you can say you can magnify it up and it almost fits. But you have to say what you mean by almost and make that technically correct. No, I drew this pattern out, and a friend of mine was in hospital, and I thought I'd like to send her something to cheer her up. So I drew this pattern and sent the pattern to her. But then it was somewhat later when I looked at this pattern, and I thought, I wonder whether you can put little knobs and notches on it to force the pattern. So you would make it as a jigsaw puzzle, which can only be assembled in that way. Now, I don't know why I thought that, but I just thought maybe you could do that. I fiddled around for a bit, and I realized that you could put knobs and notches on them, provided you have 3 different versions of the pentagon. Some of them, you can find a pentagon which has 5 others around it. You have to put knobs and notches to make that nice and symmetrical. Some of them have only 3 around it, and some of them have only 2. And you put the knobs and things differently, depending on whether it's got 5 round or 3 round or 2. And so you then have 6 different shapes. And what you could see is that this jigsaw puzzle can only be assembled in this way. So I knew that you could do that. And I was having a conversation. I think I'd only just got my job as the Rouse Ball Professor in Oxford. And I hadn't actually taken up my post yet, but there was some meeting going on prior to that. And I can't quite remember the same occasion. But anyways, I was visiting Oxford in connection with my going to go there. And I was talking to Simon Cochin, who was a Princeton mathematician. And I got into this discussion. I think I was aware of the fact that somebody had shown you could have a set of small number of shapes which would only cover the plane in a non-repeating way. And Simon Cochin was telling me that, the first version of this used over several thousand different shapes. You had to have several thousand different shapes. And with these different shapes, you could only fit them together in a way which didn't repeat. The chap who'd done this, Robert Berger, I think that was Robert Berger, he'd got it down to 106 or something. So that was the smallest he could get it down. Then Raphael Robinson had got it down to 6. And I was told that Raphael Robinson was somebody he really liked to get down to the smallest number. So 6 was the number.
Right.
And I thought, I can do it with 5. Because I knew that the piece which is it now? I think it's the star-shaped one. I had a little knob thing on that. Yes, which would only... I can't describe it without you seeing it. But I could get rid of one of the pieces by sticking 2 of them together. I knew that because of the fat matching rules, you could get the number down to 5. So I knew you could do it with 5. So then I went home and started fiddling around a bit, and I managed to get down to 4. I was pretty pleased with that. I thought 4, that's good. That was pretty good. Then I thought, I wonder whether you can get it down any smaller. And I got it down to 2. What was my reaction? Disappointment. Because I look, this is absurd. This is just too easy. Surely it's known. I don't know why the reason I thought it. I just thought it was too. The 4 one I quite like, but 2 one was just too simple. You could do it with. It was the kites and darts. It was the first one. It was a dart shape, which is like that, and a kite shape, which was. No, that's the dart shape, which is like that, and the kite shape is like. I don't know if you've got pictures there. And you can match them, and that was the first one.
Not true.
That was the first one I had with only 2, and then I could see how to do it with the rhombuses.
Right.
And so I had those 2 ways of doing it with only 2.
Well,
And I thought,
Go ahead.
Well, I thought that, there's Islamic designs, you have all sorts of complicated things with pentagons, and I'd certainly seen some of those things, complicated pictures. But as far as I'm aware, they've never rediscovered these things.
Right.
That somebody did almost rediscover them, or not rediscover, pre-discover them.
Uh-huh.
Yes, somebody did.
Right.
That was Kepler.
Uh-huh.
And in fact, I was aware, you see, my father owned a book which had two of Kepler's books together in it. And one of them was Mysterium Cosmographicum. I think it was the other one, I forgot what it's called. Anyway, in this book, you see there's a page. And in this page, you see Kepler. You don't see Kepler, you see his drawings.
Right.
These drawings of little regions of patterns made out of polygons and things like this, nice symmetrical polygons, but not the normal symmetries. You have things with octagons and decagons and things like this, and fitted together, which make nice patterns. The biggest one in that is made with pentagons and decagons, and they fit together to make this beautiful pattern. And that was obviously the one he was most proud of. It's called AA. There's a bit more to this story, because when people started to discover the quasi-crystals, which apparently had these symmetries, and I was visiting Switzerland, and I was trying to be persuaded by a chap there. They'd found not just the 10 and 5-fold ones that came from this, but also the 8-fold ones that Robert Ammann and somebody else had discovered. And this chap I was talking to had found a 12-fold one. And he was trying to convince his colleagues, and nobody would believe him. And I looked at his diffraction pattern. You shoot X-rays or whatever it is, and you can see these symmetrical patterns. And
So
I looked at
these
this
were
pattern.
experimentally verified as these quasi-crystals?
These were, sorry?
Experimentally verified. I mean, these
Experiment,
quasi-crystals.
oh yes, I'm sorry, I should have said these are experiments.
Yeah.
This was experimenter.
Now, given that we're somewhat limited on time,
I was jumping.
could we?
I just wanted to
go
say
ahead,
this
go
one
ahead.
thing, because I looked at this diffraction pattern and I thought, I've seen that before. Where did I see it before? Kepler. And it's in this picture of Kepler. I don't know if you got the Kepler.
No, we don't have that.
So that was in the Kepler picture too. Also, this biggest one, you take my pentagon pattern, I didn't know this for a while, you slide it into the right place, it matches Kepler's picture exactly.
Wow.
Right
So he
up
was
to
right
two
on the
little
cusp.
lines he's drawn in one of the decagons.
Nice.
It's stunning. I don't know what he was doing. My guess is he was trying to do something non-periodic, because he knew sort of about crystals and the symmetries, and maybe life would be something with the non-crystallographic symmetries.
Which brings us to our
Which
next
brings us
topic.
to our thing. Yeah, the problem with having conversations with a mind like Sir Roger is I wish I had 20 hours conversation.
I'm sorry.
Yeah, this is fantastic.
I couldn't tell you. I couldn't resist telling you the
In
Kepler
addition to all of the achievements in mathematics and physics, now Sir Roger has also done a lot of work in consciousness and artificial intelligence. And of course, there's a lot of excitement about this subject right now, which Sir Roger just mentioned. But you were writing these books in the 80s and 90s. I mean, how did you get interested in the subject, from aside from all that math and physics?
Well, you see that the real reason, the reason came, a lot of it came from when I was early in my graduate student work. I mean, the issue came about then. That was just my second year. Right. I can't remember if it was my first or second year. I don't know. I went to lectures on subjects that weren't anything to do with what I was doing. I was working on algebraic geometry. It was pure mathematics. Right. And I went to 3 courses of lectures. One by Hermann Bondi on general relativity, had a big influence on me, clearly. Mm-hmm. One was by Dirac, Paul Dirac, the great quantum physicist, on quantum mechanics. That had a big effect on me. The other lecture was by a man called Steen on mathematical logic. And he lectured about Turing machines, so I knew what a computation meant, and Gödel's theorem. So Gödel had this wonderful theorem. I heard about it before, and I didn't really like the idea that he seemed to have shown that there were things in mathematics that you couldn't prove. I heard the lecture, and I realized it wasn't that at all. If you have a particular system of proof procedures, and they were proof procedures that you could put on a computer, I knew what that meant. I knew what computable meant. You see, that was part of the course. That you could put it on a computer. If you can put these rules of proof, then you can formulate a sentence, a mathematical sentence, which you can see must be true if you believe that these rules of procedure only give you truths. So if you trust the proof procedures, then you know that this statement is true. You also know it is not provable by these procedures. I found that absolutely stunning, because it shows you that the way we understand the truth of things in mathematics is not following computational rules. And that a thing I formulated this view from the Steen lectures. I didn't do anything with it, but it just seemed to me that this argument that somehow you build more and more complicated computers, they're just elaborate Turing machines, that's what they are. I mean, Turing, that's what he started the whole thing up, basically. And they are doing what we call computations. But from this course of lectures, I knew that there were things you could not establish by computation. Oh, you can get a new system of proofs which can use that, but then, yeah, sure. But then how do you know the new system works? Only because of your understanding of why the original one worked. So you've got to bring in something which is not a computation, which is understanding. So I had this view that whatever understanding is, and what it is something which needs consciousness. So whatever, I mean, consciousness, there's all sorts of other things I know, of course. You know, the perception of the color green or something like that. These are conscious things. But one of the things consciousness does is to understand things. And understanding is therefore, I formed the view, not a computational procedure. Now, nobody believed me, but I was thinking, I didn't think of doing anything with that. But much later, I thought perhaps when I'm retired, old and retired, I'll write a book about it. And then Stephen Hawking was writing his book on Brief History of Time. And then I heard some people talk, this was Marvin Minsky and Edward Fredkin, and they were talking about how wonderful computers were and the ones in the future would supersede anything we can do. And I thought, well, I can see where you're coming from, but I don't believe you. So I tried to write The Emperor's New Mind, and in the process, find out what it was in the brain which could be non-computational. Well, I believe from the Dirac talks, actually, that it had to be, I was just in the process of elimination. It couldn't be Newtonian mechanics, it couldn't be general relativity, it couldn't be ordinary quantum mechanics, I understand it. It had to be something missing from the theory. And what's missing is this thing called the collapse of the wave function. I don't know how much you wanted to ask me about this, but I did form that view that there was something missing in Dirac's talk. It made it clear to me. But he wasn't trying to emphasize the talk. It was more the following. He was getting to the point. He's talking about quantum mechanics. And you can have, in quantum mechanics, you can have a proton can be here, or it can be here, or it can be here and here at the same time, in different ways, here and here at the same time. Then he took out a piece of chalk and he broke it in two or something. My mind was wandering. I was looking out of the window or something. I don't know what he was saying. When my mind came back to what he was saying, he moved on to the next subject. So I thought, why on earth can't a piece of chalk be in two places at once? If I'd heard him, he probably would have said something to calm me down and stop me worrying. But I didn't hear him, or I didn't remember, so it stuck with me all the time. There must be something in quantum mechanics which goes beyond the Schrödinger equation, which goes beyond the framework of... I didn't know much until much later that Dirac thought exactly the same thing, but I only learned that much later. Schrödinger thought the same thing as Dirac too, as did Einstein, but many people thought that quantum mechanics is all the answers. But I thought, no, there's got to be something else going on, which is called the collapse of the wave function. And then I tried to write this book, The Emperor's New Mind, to find out enough about how the brain works so I'd see where this comes in. So I read about neurophysiology and I found about a Hodgkin-Huxley nerve transmission, and I thought there's no chance in hell. The signals as they go down the nerves disturb the environment too much. You can't preserve a quantum coherence like this. So I hadn't any idea at all. So I kind of fudged the way out to the end of the book, saying something about quasicrystals, and maybe there's a similarity there. I don't know. Well, maybe there is, but I didn't really believe what I was saying at that point. But then You see, I got lots of letters. I thought it would be nice to have lots of letters from young people doing their research, and that would be nice. What did I get? Lots of letters from retired people. These were the people who had time to read my book and write about it.
Well, speaking of letters, I mean, there was an open letter by Elon Musk and Hawking on challenging the singularity. I mean, this possibility of the singularity, technological singularity, not your singularity.
Oh.
And there was this open letter about the
mean.
rise of the, we're doomed to
people call
failure.
singularity, yes,
So you're a big skeptic of this, obviously.
Yes, but you have to be careful about what I'm a skeptic of. You see, it's not a computer. It's not in that sense. It doesn't mean that we might not someday, that some latter-day Frankenstein will see how to incorporate the right structures and make a conscious being. I don't say that's impossible. I just say it's not a computer.
Oh, I see.
But you see, the argument is that you have to incorporate the collapse of the wave function in an active way. And I couldn't see how neurons did it. Then one of the letters, which wasn't from an old retired person, it was from Stuart Hameroff, who was a neurophysiologist, but mainly he was his job was to put people to sleep. So he was name's got out of my head, an anesthetist or anesthesiologist, as they call it in the States, and that was his job. But not like most of his colleagues who just wanted to make sure they were able to wake the people up afterwards and they didn't cause them pain, things like that. But Stuart was really interested in what on earth is he doing when he's putting them to sleep. He also emphasizes the wrong term because it's not sleep. They're unconscious, but it's not really sleep. It's something different. But his view, which he'd formed for quite different reasons, that it had to do with these little structures called microtubules. And he wrote them to me, and I thought, oh, not another letter from a crackpot, you see. And what are these things he's talking about? These microtubules, what are they? So I looked up. Oh, he's right. And they were beautiful symmetrical structures, I thought. And so there's a much better chance. Here you might be able to preserve quantum coherence at a level which could perhaps preserve coherence. You see, you need to have a quantum state which remains undisturbed, doesn't leak out into the environment, coherent in a certain way to such a level that when the collapse of the wave function happens, it happens in a way which is usable. So the idea was, and we formulated this idea that we call orchestrated objective reduction. You see, it's not just the collapse of the wave function, because that's happening all the time, but it's got to be orchestrated in a way and made use of by the microtubules and by structures in the brain. And that's the scheme that we've been working on for decades now.
So Roger, this quantum phenomena that you're talking about and looking to describe is a potential way out or a potential way to explain a way out of humans having non-algorithmic insights.
Yes, well, the argument is that whatever it is that happens, you see, it depends on, it's absurd, because it doesn't just depend on changing neurophysiology, it depends on changing physics. And that's, sometimes people get very confused. They say, oh, we're saying that quantum effects are happening in the brain. Oh, no way could that be true. We're saying much worse than that. We're saying it's not quantum mechanics, it's where quantum mechanics goes wrong.
Right.
Does quantum mechanics go wrong? Most people don't think that. Well, you see, it's the collapse of the wave function. It's one of these very curious things. You see, Schrödinger, he understood better than anybody because he introduced this thing called what people call Schrödinger's cat. And the argument is that you have this cat in the box and you can put the cat into a state of being dead and alive at the same time. Now, Schrödinger was not saying, look, if you made this box and you put it like this, and you can make a cat which is dead and alive at the same time. He wasn't saying that. He was saying, this is an absurdity. A lot of other people say, no, maybe you could make a Schrödinger's cat and do it, blah, 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 blah. Schrödinger was trying to say, look, this is where Schrödinger talking, my equation goes wrong. He was never quite putting it as blatantly as that. But roughly speaking, he was saying his equation is not governing the way the world operates. It goes along as long as you keep it isolated and whatever it is. You have to be careful because different people have different theories about this. whatever it is, where this thing called the collapse of the wave function, that is, you follow Schrödinger equation, this is following the wave equation, Schrödinger equation tells you it does this, 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 and this. You can put that on a computer. Yeah, you can put that on a computer. And then it doesn't do it, it collapses. That's usually what you call making a measurement.
Before we run out of time, we've got a little bit of time left, but
Yes.
one of the things that Yang and I, we agree on almost everything, but the one thing we completely disagree on is the future of AI. I'm a great skeptic,
Yes.
and Yang is a fan.
I'm a fan. I
you
wouldn't
know,
say fanatic, but I'm a fan.
Yeah. So in particular, sort of the role of artificial intelligence or advanced computation, machine learning, whatever you want to call it, the role of that in enhancing human creativity. So in particular, automated, conjecture formation or creative acts, or even, Yang, as you like to think about, automated proofs. And so, some of the evidence for that is, systems. We've got a slide now about AlphaGo, and then there's AlphaZero.
Right.
And I think somebody in the audience here is one of the developers of AlphaGo.
Sure.
What's your sense on the role of computation, machine learning to enhance our creativity?
Oh, that's a difficult one. You see, you might explore the implications of something using a computer, which is what people do all the time now. You may have some idea about what's going on, and then you test it by computation. And a lot of physics is like that now. Sure, that's fine. There's nothing wrong with that. The question is whether you're making the computer creative. Now, what does it mean to be creative? You can certainly make it do things you hadn't thought of before. Now, is that creative? Well, I don't know. It's not usefully creative. It might by chance, you see. Well, it does this protein folding thing now, which, of course, that people have found it's very good at doing protein folding. Maybe. I don't like to... See, creative is a word that's rather hard to pin down, I think. I prefer to use the word understanding. There, you see, I think it's much clearer, because you couldn't say AlphaGo understands anything. I say I have an idea about how to... This is a nice challenge. I'd like to do it sometime. To see whether... I don't know whether it would work, but you might be able to defeat AlphaGo and whatever it is, Alpha Plus, whatever these things are called. Be an interesting challenge. I won't talk about it now because I don't want too many people to think of it ahead of time. But it is a way that... sure, it beat the world champion, but that's in the normal way you play Go, which starts with an empty board. So the idea would be to modify the game a bit. You see, the thing about making a very good Go player, that it's very clear what the aim is. You can tell who wins. So you can make it play itself a zillion times, and without understanding a damn thing, it can play itself a zillion times. And it knows which one wins, when it wins. And so it's clear what wins means. Now, it'd be very different if you have something which is not clear what the objective is. If it's got a clear objective like that, then maybe, yes, you can make a computer do it better than a human being, which is what happens with Go. That's right. But does it understand what it's doing? I think one could make a case that it doesn't. But I'd like to... that's a challenge which I had in mind using. Now, I had this thing with chess, which you could do that.
Right. But there's a growing community within the mathematics community who, sort of saying that, this analogy of mathematics being like chess, and this community thinks that we can, within the next few decades, AI, or the likes of AlphaZero, would start proving theorems and raising new conjectures in mathematics that are better and faster than us. So what do you think of?
It's possible. You see, I'm not arguing against that, really.
Okay.
I'm just saying it doesn't understand what it's doing.
Right. So even though it's produced a correct proof of a correct theorem.
Yeah, sure. Well, there's examples of this. The four-color problem. There's a proof. I used to waste a lot of time on trying to prove the four.
Right, I see.
The four-color problem is proved. I believe now there is no proof at the moment which doesn't at some stage use a computer.
Exactly.
Now, does that computer have the faintest idea what it's doing? No.
I see.
Do we know why that calculation gives you a proof of a four-color problem? No. And not unless you follow the argument. What is following the argument? You've got to understand it. You've got to know what it means. Now, it doesn't mean that you can't take advantage of having the computers. That's what people do, and that's what they're for. But the question here is maybe it would find something, some clever little thing that nobody had really thought of, and a proof of it, I suppose. I don't see that's impossible. It's a bit sort of, well, there is a thing which, there's a little joke in one of my books. I don't know if anybody's seen it yet. Can tell you the joke, yes.
Please.
There's a picture, I think it's in Shadows of the Mind, yes. There's a picture which is illustrating this understanding point, where it's got a picture of all our ancestors doing all sorts of wonderful things. There's in the foreground, you see the mathematician who's trying to prove a theorem. And he's completely devoted to try and prove this theorem. And there's a saber-toothed tiger just about to pounce on him and eat him up, you see. So what I'm trying to say is that's not selected for. What is selected for is these people who build a wonderful mammoth trap. And you see the poor mammoth getting rather disturbed. He's about to fall into the trap. And you can see people building shelters in the distance and growing crops and domesticating animals and using their understanding. And that's why the concept of understanding with this universal quality was selected for, and consciousness was something which was developed in human beings. Nothing purely for doing mathematics and seeing how to do theorems which can't be proved by simple axioms and things like that. Now there are examples like this, and I give this in the book. I think I do in that book. I can't remember what's in the book now. But anyway, what I'm trying to say is that the quality of understanding is something which uses consciousness. And understanding is something which is very broad in its applicability, and it has a very, very essential role to play in mathematics. Now, the example I think the Goodstein example is in Shadows of the Mind. That's a very nice example. You can explain to people who don't know very much mathematics, and it's a thing you can't prove by ordinary induction, which is you learn that in school, how to prove. You can prove something is true for all n. And the way of doing it is using mathematical induction. But the Goodstein theorem is being shown you can't prove that by mathematical induction. Yet we know it's true. Now, how do we know it's true? Well, we can't have done it by, maybe these ancestors of ours could have formulated the idea of mathematical induction. But they can't have thought, what's the use to evolution of thinking of transfinite induction? That's what Cantor did. That's what you need to prove the Goodstein. You need transfinite induction. Okay, you can understand. You don't have to be Cantor to understand it. You don't need the genius of Cantor. Maybe he was a fluke and somehow could think of this. No, you just follow the argument. And you say, I see, that works. Yes, it's true. Now, how do we have the ability to see that when the algorithms, if they were just algorithms, that we use to develop our abilities, well, in fact, were just algorithms. We have to have something beyond algorithms which enables us to understand things. Now, I'm not saying that won't be achieved by future technology. I'm glad that I won't be around when that future technology comes about. But sure, there might be some, as I say, a latter-day Frankenstein who can create a conscious being. Maybe it can happen. But it's not just by computation. You have to take advantage, according to me anyway, take advantage of whatever is going on in this part of physics that we don't understand yet, which is the collapse of the wave function. And somehow nature has done it already by itself.
So I've read early on, as a teenager, your first book up there, Members in Mind, and then more recently, this year I read your second book, where you sort of Shadows.
Yes, that's right.
I find these books more relevant today than ever before. I mean, so many people are debating, and I've had so many of these debates, and we've had these debates about the sort of brave new world of what could happen. And I find it's one of these little miracles to see that argument, to know that we know truths which are non-algorithmic, right? Cannot be done on any sort of computing device. But where I thought we've got a little bit of time for questions from the audience.
Okay.
And I thought we might stop there, just the three of us, and invite some questions from the audience. But thank you so much. We could go on, as you all know.
20 hours.
But thanks so much for joining us. It's been a real pleasure to have you here.